Today I'll be going over my lab report for Lab 4, which involves analyzing a mass on a spring going through oscillation. The experiment involves observing a mass in oscillatory motion. The ultimate purpose is to create graphs to depict the positions and the potential and kinetic energy of the oscillating mass on the spring. The tracker software created an X position versus time graph and a Y position versus time graph based on the video of an oscillating mass attached to a spring. The GlowScript makes a comparison between the tracker graph and the predicted model graph. Additionally, GlowScript creates a graph that plots the energies involved in the oscillation against time. Now let's dive deeper into the core concepts of the lab. Oscillatory motion is defined as a periodic motion around an equilibrium or central point. The equations used to calculate different components of oscillatory motion are shown on the slide. The mass of the spring undergoes two kinds of forces. The first force, the force of gravity, applies to all objects on the surface of the Earth and can be calculated using the formula mass times the g gravitational constant. The spring force is created when spring compresses or stretches and is calculated by multiplying the k constant value by the length of the compression or stretch times the normal vector of the stretch. Additionally, energies are calculated during the oscillation, and the energies in action in this experiment is spring potential, gravitational potential, and kinetic energy. In both the experimental settings, the mass was 0.402 kilograms, and the K constant value was 6.83 newtons per meter, and the relaxed length of the spring was 0.123 meters. In the GlowScript model simulation, delta T was 1 divided by 210 seconds, and the tracker software used the delta T 0.095 seconds. The system solely included the mass, while the surroundings are the Earth and the spring attached to the mass. When creating the modeled prediction, GlowScript was used to code the simulation for this experiment. The initial position of the ball and the spring, the K value, and the delta R are all instantiated. The position and velocity update formulas are used to graph the position time and velocity time graphs. The position update formula is initial position plus velocity times delta T, and the velocity update formula is initial velocity plus F net divided by mass times delta T. The code used iteration to create an accurate position versus time graph. F net is calculated using the spring force and the gravitational force. Additionally, the code calculated the kinetic spring potential, gravitational potential, and total energy at each timestamp. The graphs of the trajectories are featured on the slide. In the actual experiment, Tracker was the graphing software used to plot the actual data. A video was taken of a mass being set into oscillation. We uploaded the video into the tracker and trimmed it so the video only included the part where the object was in oscillatory motion. We set the position axes with the origin being at the center of the mass at its initial position. Tracker was able to create a sinusoidal graph for the X position versus time graph and the Y position versus time graphs, indicating that the mass went through oscillatory motion. Now moving on to comparison. The two graphs were similar in terms of having sinusoidal curves and having about the same amplitude for the X position versus time graphs. The main difference comes from the Y position versus time graphs. A source of error that could have led to these differences is the possibility that the video uploaded into Tracker was calibrated incorrectly, which led to incorrect measurements of Y position, thus accounting for the exaggerated amplitude of the experimental Y position versus time graph. So what does this mean? Does the tracker model follow the energy principle? Yes, it does, since the change in the energy throughout the experiment remains zero, which indicates that energy is conserved throughout the experiment. Additionally, the kinetic energy, spring potential energy, and the gravitational potential energy always add up to zero. My estimation for the period of the X position versus time oscillation was about 2.41 seconds, since the graph went on for 9.622 seconds and there were 4 oscillations, which means that one oscillation took about 2.41 seconds. My estimation for the period of the Y position versus time graph was 1.6 seconds, since the entire graph went for 9.622 seconds and 6 oscillations took place, which means that each oscillation was about 1.6 seconds. So finally, in conclusion, a sinusoidal position graph is created by the model prediction and the tracker software of the spring's oscillation. We know that the energy principle is satisfied throughout the spring's oscillation since delta E remains zero throughout the graph. Both the modeled prediction graph and the tracker graphs follow that sinusoidal regression, which confirms oscillation. Thank you for listening.